Okay, so now that we know about the valence shells and the ability to fiddle with the electrons in it, we have to talk about bonds. These are different types of bonds, covalent, ionic, and hydrogen, but they all involve interactions with electrons. Atoms and molecules can share electrons, or you could just outright donate an electron to another atom or molecule. Conversely, you can outright just get as a gift an electron from another atom and molecule. So when bonds are formed, they trap energy in them. When bonds are broken, that energy then becomes available for use. Think of the picture of this water molecule here, right? It's kind of like a head of a Mickey Mouse. So you have the face, which is oxygen, and then you have the ears, which are hydrogens. One molecule of water has two covalent bonds that join each hydrogen atom to the oxygen atom. Listen to that again. One molecule of water, which is the entire Mickey Mouse head, one molecule of water has two hydrogen atoms covalently bonded to an oxygen atom. This is usually where students are like, whoa, I didn't have a good definition of atom and molecule. Right, so a covalent bond or an ionic bond or hydrogen bond can bond together atoms and create a molecule. The problem here with Mickey Mouse is that the oxygen atom has a greater affinity or attraction for the electrons than a hydrogen atom does. Right? And this does make sense. It totally makes sense because the oxygen has 8 protons in its nucleus, and either one of the hydrogens, even combined, the hydrogens only have 1/4 of the attractive power of the oxygen with its 8 protons. And so what ends up happening is that all of the electrons, they kind of like have this little party down here by the chin of the Mickey Mouse heads. And so most of these electrons, even these two, they all spend time down here, and nobody likes to spend time out here in the Mickey Mouse ears because there's nothing to be attracted to out there, right? So thinking about this, that even in a molecule, the nucleus of an atom can draw the electrons to it and create an electron party at one place on an enormous molecule. A covalent bond consists of a pair of shared electrons, like hand holding instead of just standing next to each other. There's no movement of electrons. There's no trading or receiving or gifting from an atom to another or an ion to another. And the sharing, it creates this like super valence shell that surrounds both of the atoms or all of the atoms involved. The supervalence shell provides each of the atoms with the correct number of electrons, but it also provides the other ones because they're all sharing them. So it's like each nucleus is like, oh, I'll just count those to be mine. Okay, so take a look at the diagrams here. Take a look at oxygen over on the right-hand side. The red dots are the electrons that are in the valence shell, only the valence shell. And these are really common diagrams that are like abbreviations. This box consists of, all of these boxes consist of the shared electrons. So when two oxygen atoms come together, they share two pairs of electrons to make a double covalent bond. And this is what we call molecular oxygen. This is what you're taking in from the air right now, not oxygen atoms, but oxygen molecules. On the bottom of this picture, we have water, or H2O. And the hydrogen atoms in water are bonded by a single covalent bond to the oxygen atom, right? Each one has its own single covalent bond. And each of these single covalent bonds are weaker than the double covalent bonds together. The more electrons you share, the stronger the bond is. This unequal sharing of electrons creates two separate areas of electrical charge. Over here on water, or Mickey Mouse, the oxygen atom, or Mickey Mouse's chin, the molecule is partially negative charged with more electrons down here more of the time. They just like to spend their time down here. It's like an electron party. Around the hydrogen atoms, or up by the ears, the molecule is partially positively charged. Partially positively charged, because the electrons, they go up there, but they spend less time there. This type of bond over here between the atoms of a water molecule is called a polar covalent bond. A molecule with two poles, one slightly negative and one slightly positive, north and south. No, you just positive and negative, not north and south. Many students try to find an association to polar molecules with their charged poles to the magnetically charged north and south poles of the Earth, or the positive and negative poles of a magnet. You're not wrong. A polar substance with both positive and negatively charged poles is in contrast to a non-polar substance which has no charge anywhere around it. Students sometimes have a common misconception here about polar and non-polar. They sometimes think that polar means positive and non-polar means negative. Incorrect. Polar is a word that refers to both positive and negative. So you are charged. And this polarity results from an unequal sharing of electrons. Non-polar, atoms that are involved in non-polar bonds, they share their electrons equally. And so non-polar molecules have no charge whatsoever. None. Like a block of wood, not like an end of a magnet, right? Or like Princess Leia here. So we have Mickey Mouse and Princess Leia. I'm kidding. Over here, this is carbon dioxide, and it is a non-polar molecule, like oxygen is also a non-polar molecule. Okay, so participants in polar covalent bonding can share their electrons equally. On the left, we have carbon dioxide, right, shaped like Princess Leia had with her braid buns. Carbon is equally sharing its electrons with the oxygens. It's like, oh, okay, we can all share equally. Like, you can have one, I can have one, we're good. We can also see that there are two gray connecting lines between carbon and oxygen, and this is what indicates to us on diagrams like this a double covalent bond. When electrons are shared equally, such as in carbon dioxide, we call this nonpolar covalent bonding. It's nonpolar because no one area of the molecule has any type of charge, negative or positive. On the right is water, which does not equally share its electrons. All right, so now Princess Leia's braid buns have just been moved to the top sides of her head. And with that, we get Mickey Mouse. And what we're going to find out, and a good word to use, is that an oxygen atom has a greater affinity or attraction for electrons than a hydrogen atom does. And this makes sense because an oxygen atom has 8 protons, whereas a hydrogen atom only has 1 proton. Oop, I don't want to put a T there. That's not points, that's protons. So if a hydrogen and oxygen atoms share electrons, the electrons are definitely going to spend more time around the oxygen. And we can think of this, as I said before, like in a little electron party. The significance here, it'll attack us continually in this course. Nonpolar molecules versus polar molecules is an incredibly important concept because, as the same saying goes, like dissolves like. This means that polar substances will dissolve in other polar substances. Okay, right? Okay, like dissolves like. And non-polar substances will also always dissolve other non-polar substances. I guess we could say that oil, a non-polar substance, and water, a polar substance, they don't mix, right? And because you are a water-based organism with water as the basis of your blood, this can have effects on the solubility of things in your blood. For example, estrogen, testosterone, and other important hormones are non-polar or hydrophobic, like cortisol. How do they travel in your blood? Right? If they're non-polar and your blood's polar, well, they do it attached to a protein. And this protein, what it does is it creates a hydrophilic complex that's able to dissolve into blood. Just one note. If you want to get an oil stain out of a cotton shirt, right? Oil, non-polar, cotton shirt, polar, you have to use a non-polar substance to lift the oil out. Baby powder is a non-polar substance, and it does this trick wonderfully. I know because I am a messy eater.